This is where our project ideas come from. Imagine that you see an object like this, and of course you can recognize it as a tomato. This is because, in your retina, your cones bring in its red and green color, and your rods detect a smooth, round contour. Then imagine that your lights are dark. Your cones are not working, so that you can only see an almost grayscale tomato. You can still recognize it as a tomato, not a banana, because you can still see its unique shape. We believe that a neural network can also achieve this. Even if we throw away its input color information and the corresponding neurons inside the model, it can still achieve a relatively high classification accuracy.
Hi everyone, welcome to our screencast. My name is Francis, and my teammates are Guanzhong Chen, Shi Yuliu, Cangchen Tang, and Zhi Wang. In this video, my team, Canned Pineapple, will introduce our project about how we adapted image recognition models to work more optimally on grayscale pictures using pattern-specific receptive fields. You probably are wondering what receptive field means. It refers to the part of the image that is visible to one filter at a time in a convolutional neural network. By the way, our team name, Canned Pineapple, is based on a Hong Kong film that we like. Here are the contents we will cover in this video. We will firstly give you a brief intro of the project background and dataset. Then, we will present two trials we made using ResNet and DenseNet. Since results shows DenseNet outperformed ResNet, our final compressed model is based on DenseNet. How did we get this project idea? In studies of image recognition, there are many grayscale pictures, such as chest radiographs, as shown on this slide. Currently, the idea behind training those images is to apply models that are essentially designed for training color pictures, such as ResNet and DenseNet. This can lead to many redundant parameters during the process. Therefore, this project aimed to discover a methodology to modify the models trained on colored images and to apply them to grayscale images. In order to simplify the training process, this project used the CIFAR-10 dataset, which you probably know already. It consists of 60,000 32 by 32 pixels color images in 10 classes, with 6,000 images per class. Also, the training to testing ratio is 5:1. The figure on the left shows a group of color images from the original dataset. Then, the color images were converted to grayscale images by adding linear weights to the RGB channel values. The figure on the right shows another group of grayscale images after this transformation. Next, Guanzhong will walk you through our first trial, ResNet.
Hi, my name is Guanzhong Chen. I'm going to introduce ResNet to you. Let's look at ResNet's architecture. Each residual unit is defined to be composed of two convolutional layers with batch normalization and ReLU activation, using 3x3 kernels and preserving spatial dimensions. The deep residual network can be seen as a stack of residual units, where each residual unit is a small neural network with a skip connection. After understanding ResNet, we apply ResNet on CIFAR-10 dataset. Here is the algorithm. First of all, we train both colored and grayscale images using ResNet from scratch. Note that the input of grayscale training is a triple of the same information so that it can be fit into the model. Next, we use original pre-trained weights on both colored and grayscale image training processes. Specifically, we want to fix the weights of convolutional layers and fine-tune the weights of dense layers. As the table shows, after 50 epochs, without pre-trained weights, the accuracy increased by 0.05% from colored image to grayscale image, while with pre-trained weights, the accuracy decreased by 3%. This means that in the case of no pre-trained weights, whether or not the image is colored does not affect the final accuracy. If pre-trained weights are applied, the model performs better on the colored image. We also modify ResNet structure with the input layer accepting only a single piece of information, that is one channel input. The results on grayscale image are not as good as others. Next, Zhi will introduce us more about our work.
Hello everyone, I'm Zhi Wang. Let's take a look on DenseNet model in next few minutes. I want to share our DenseNet architectures table first. DenseNet contains a feature layer capturing low-level features from images, several dense blocks, and transition layers between adjacent dense blocks. In the dense block, it is easy to see the width and height of the feature maps keep the same through the dense layer, which makes it easy to stack any number of dense layers together to build a dense block. For example, the DenseNet we built has 4 dense blocks. Each has 12 dense layers respectively. As a tradition, the size of output of every layer in CNN decreases in order to abstract higher level features. In DenseNet, the transition layers take this responsibility, while the dense blocks keep the size and the depth. Every transition layer contains a 1x1 convolution layer and a 2x2 average pooling layer with a stride of 2 to reduce the size to the half. Be aware that transition layers also receive odd outputs from all the layers of its last dense block. So the 1x1 convolution layer reduces the depth to a fixed number, while the average pooling reduces the size. These two plots show the depth of each block. The input for color images is 3 channels and 1 for grayscale. 18 in the transition layer here is the depth fixed number I just mentioned. If you are interested in more details on the model architectures, welcome check our notebook at GitHub. Next, let's check the accuracy on CFI 10. All results from the models without pre-trained weights, and a training for 50 epochs. Each epoch is about 2 minutes to train. Definitely, color image has the highest accuracy. Then is the grayscale images with 1 channel. The worst is the grayscale with 3 channel. We would use DenseNet pre-weights, which is trained by color images with 190 epochs, and the accuracy is 91.16%.
Hi everyone, this is Shiyu. I'll be introducing visualizing and clustering filters. After our DenseNet model has been trained for 190 epochs on Cypher10 dataset, it has reached an accuracy over 90%. What if we directly input grayscale images to this model? The result is quite promising, 83%. This model is supposed to utilize the color information, but there is actually no color input if we use such grayscale Cypher10 images. We want to prune some of the filters that are in charge of the color information, and if possible, we can also combine the filters that are in charge of the same pattern to compress our DenseNet layers. So, we start investigating the filters. To detect the receptive fields that each filter is meant to respond to, we used an algorithm called gradient ascent in input space to visualize them. We apply gradient ascent to the value of the input image of a convolution layer to maximize the response of a specific filter. We start the input image with noises, and we use the mean of the output pixel activations as loss. After plenty of steps of stochastic gradient descent, the input image will be the receptive fields that the chosen filter is maximally responsive to. Take our first convolutional layer as an example. The 36 receptive fields are shown here. The first filter is sensitive to green, and the 7th filter, below it, is mostly responsive to dark blue. We can see that all of the filters in this layer are responsive to the colors only, as there is no pattern detected among these receptive fields. Since our Cypher10 image will be grayscale, we weighted the RGB channel to visualize the left colorful receptive fields as grayscale on the right. We can find that the first layer filter do discriminate the brightness for inputs. So we conclude that the first layer is only separating colors and brightness, but keeping all of the patterns for the following layers. Then let's walk through another example for the second and 14th convolution layer, which locates at the beginning and after the end of the first dense block. This time, we can clearly see that specific filters are responsive to particular type of patterns, while the shallow layers can detect both brightness difference and simple patterns. Deep layers start ignoring brightness, but focus more on complex patterns. After such filters have been visualized, we start to cluster them. First of all, to represent our filters, we use the receptive fields for each of them. That is, we cluster the filters based on these input images, which can be represented as a 32 by 32 matrix. Then we need to calculate the distance between each pair of these receptive fields as a measurement of their similarity. For the first convolution layer completely focusing on brightness, we use MSE method to calculate the distance. For the following layers that focus more on image patterns, we tried structural similarity index and image Euclidean distance. These two distances consider the relative pixel position when calculating the value difference between different pixels. Then, we use the dbScan algorithm for clustering. We're using this dbScan method instead of k-means because it is not influenced by the outlier, and our data contains some noises. For the first layer, the result is quite intuitive based on the brightness. For example, the dark blue ones with less noise are clustered to group 6, and lighter ones are clustered to group 7 and 13. When it comes to the following field layer filters, starting focusing on patterns, both SSIM and IMED provided similar clustering results. However, this is not consistent as what we visualized, because we can find that these three filters on the upper left corner are clustered together. They're all clustered to group 0. Actually, they look pretty different. Then Changchun will talk about how we merged filters based on this clustering result.
Hi, this is Tang. I'm going to talk about the pipeline we designed to merge the filters. What we see here is an overly simplified CNN structure. This model is designed to handle colored images with 3 input channels, red, green, and blue. So the filters of the first comp layer have a height of 3, and there are 4 filters in it to retrieve color information. But we don't have any color information in grayscale images, therefore we can shrink the model by merging the filters, according to the clustering method Xu just mentioned. But how do we merge these filters given their clusters? Well, every filter is a 3-dimensional tensor, and our example here in layer 1 is a 3 by 3 by 3 cube. Since grayscale images only have 1 channel, we start by reduce sum over the height in each of the 4 filters. Now our filters are flat, only have the height of 1. The next step is to average the filters in the same cluster. Here we put the first 2 and the last 2 filters in the same cluster, and simply average them. Now our first layer only has 2 filters with the height of 1. However, doing this also reduced the number of output channels and caused shape mismatch in the next layer. Therefore, in layer 2, the weights in each filter are added across the height according to how we clustered in the previous layer. Specifically, in the first layer, we put the first 2 and last 2 filters together, so we sum over level 1 and 2, and then 3 and 4. Now the height is reduced to 2 and the dimension matched between output 1 and layer 2. If we did everything right, output 2 in these 2 models should be basically the same. And after merging the first layer, we got a much simpler model with fewer parameters in both layer 1 and layer 2. So this pipeline can preserve most of the image pattern information, but there is another important layer in DenseNet, batch normalization. In these layers, output is first standardized and then scaled by gamma and shifted by beta. But what do they do to our feature maps? Well, we can view them as adjusting contrast and brightness. However, these features are not represented in gradient ascent results, and they are hard to cluster. Therefore, these parameters were re-estimated by only training the batch normalization layer for 1 epoch, just to let it know the correct contrast and brightness. And next, let's see how we did. All of our training and testing are performed on the Cyber 10 dataset with DenseNet. We have made two versions of our clustered model. One had its first layer clustered and another had its first and second layer clustered. The original weights of these two models come from a pre-trained densenet on color images. Its accuracy is 91.16 on color images and 83.2 on grayscale images. These two accuracies serve as our baselines. Our clustered model's accuracies are about 85%, which is lower than color model on color image, but this is understandable, as there is some information loss when we transform color images to grayscale images. But if we compare the modified models with our second baseline, 83.2% here, we outperformed it by 1.6 and 2.2, and the number of parameters reduced by 45,000. The results show that the pipeline we designed can effectively prune a model pre-trained on color images, making it perform better on grayscale. Despite that, there are a lot of grayscale images on document scans, old image copies, and medical data like X-ray scans. Almost all famous CNN models have been trained on color images. Our method can be useful in transferring these pre-trained models to work better on grayscale datasets. Next, Francis will talk about limitations and improvements.
Hi, this is Francis again. At the end of the project, we identified some limitations and potential solutions. The first limitation is that, depending on the method of clustering and merging filters, the information loss during the process can be significant. The corresponding solution is to tune the threshold value and change the way of distance measurement and filter clustering. The second limitation is that the gradient ascent gives slightly different results every time, so uncertainty exists in this process. The corresponding solution is to take the average output over multiple ascent results. Thank you for your attention. Here is some extra information if you are interested in learning more about our project.